All right. So, constantly saying the phrase the most general antiderivative and things like that get a bit exhausting. The notation becomes tedious, and we really need a better way to refer to that. And the way we do that is with what we call an indefinite integral, right? So an indefinite integral here will be, right? We write this symbol. It sort of looks like a really long, stretched out S. If you're familiar with things like, violins, it looks like sort of an F hole on a violin. Anyway, so an indefinite integral. So if we want to write down the antiderivative of f of x, right? Oops. Really zoomed in there. What we would write down is integral of f of x dx. Right? Now, right now, this dx is it's just notation at the moment. We'll talk about soon what this really needs to mean, but it is important that this be here. Right? You cannot leave off this dx. Right? This must be here. Okay? So when we write this, then, okay, well, this is f of x plus c. Right? So here we still have, the derivative of capital F should be little f. Right? So it's saying kind of like, this is notation for the most general antiderivative. So as a matter of fact, we could sort of use indefinite integral and antiderivative as synonyms of each other, right? Okay. Right, so I want to specify here, just a little bit of technicality here. So when we take an indefinite integral of some function, little f of x, we can write down any antiderivative we want, right? Any specific one. It can be the nicest one. It can be one that you're particularly fond of. It doesn't really matter. We just need to pick any one we want and then add c to it, right? Add this arbitrary constant. Okay? So now that we're talking about, antiderivatives, we need to start talking about some properties of it, right? So some things you might expect here is, well, the antiderivative of f prime of x, right? If I take the antiderivative of the derivative, what do you think we should get? Right? It's called an antiderivative for a reason, so we should probably get f of x back. But because we're looking for the most general antiderivative, we actually still have to add this plus c here. So an integral, an indefinite integral here, it doesn't exactly undo a derivative. It sort of undoes it and a little bit more. Right? And likewise here, what if we differentiate the integral of f of x dx? Well, to get this answer is actually right here. Right? This inside here would be capital F, and the derivative of capital F is little f. So this one is f of x. So it kind of says that, d dx and integral dx these are sort of inverse operations. Right? They cancel out in one direction, and they almost cancel out in the other direction. Right? And again, this should make sense. We're calling one an anti of the other. Okay. So what are some other properties then that should make sense to be true? Well, if we think about derivatives, right, we could ask, well, I know that if I take two functions and I add or subtract them, when I take the derivative, I can just add or subtract the derivatives. Well, if we just sort of think that process through backwards, we then also know that, well, to take the antiderivative of a sum or difference of two things, we just find an antiderivative of f, find an antiderivative of g, and then add or subtract them and add our arbitrary constant. Likewise, right, we talked before about, well, what about a constant times a function? Right? We know we can factor constants out of a derivative. In fact, we just used that in the last video. Well, if you think about it, when we do an antiderivative, we can just factor out that constant. Now you might think, I don't have k times c here. Now, yeah, sure, you could write these parentheses and distribute it. Right? We could write this, but what do we have here? What's going on right here? Okay, we have some number, k is just some number, times an arbitrary constant, so times some other number that I've not specified. When I multiply these two things together, what do I really get? I get another number that I've just not specified. So I may as well just call that c again, right? And so there's that's why it keeps zooming in. I keep hitting the zoom down here. So that's what's really happening here. So there's no reason to multiply the c by the constant, right? Just write kf times c. Right? So just go straight from here to here. So now that we've got some properties, let's think of some derivatives that we know, and let's think about turning them around. Right? Let's think of some basic derivatives. So, for example, we know that the derivative of a constant, let me use k here for constant. Actually, I'm gonna make it a capital C. We know that the derivative of any constant is 0. So, when we take the integral of 0, well, it should make sense that we expect an arbitrary constant, right? And again, you want to think like, all right, if I did the derivative of this and I got 0, then 0, our integrating 0, should give me back this thing plus an arbitrary constant. But it already was an arbitrary constant, so we're good, right? As sort of the next step, let's think about just one step up from a constant, just k times x. Right? We know the derivative of that is k. So when we integrate just k, it should make sense that we'd get k times x. Right? This x should match whatever comes after the d here, plus c. I think I didn't say this quite in the last slide here. Let me scroll back here. This notation up here, we should read this as this part here. We should read that as the integral of f with respect to x. Right, maybe I should actually write that out. This is the integral of f with respect to x. Okay. All right. So now that we've got that, let's look at some more stuff now. Okay. Let's look at one of our favorite rules of differentiation, the derivative of x to the n. Okay. So actually, let me alter it just a little bit. Right, I'm going to put an n plus 1 here. Right? And then when I differentiate this, we then know that we get n plus 1 times x to the n. Now it's important here to remember that n is not -1 in this example. Okay? It doesn't apply in that case because that would be x to the 0, and that's a whole different situation. So looking at this, I actually want to just look at, well, what's the integral of x to the n? Okay. So think of this rule we have over here. Right? If we integrate a constant times something, we just get k times that. So what that ends up meaning here, and this goes back to the first example we did, when we integrate this, we're actually going to add 1 to the power, okay? And then we're going to end up dividing by the new power, plus c. And this should kind of make sense, right? When we do the derivative, we multiply by the old power, and then we subtract 1. For an integral, we're going to do the opposite of both of those things. We're going to add 1 to the power, and we're going to divide by the new power. So, once we have this, let me emphasize here that n is not -1. Right? It's very important to add this in here, because if n were -1, we'd be dividing by 0. So, well, what does happen if n is -1? Right? Well, let's think about it. Do we know a function whose derivative is x to the -1? Well, we do. Right? If we think about the derivative of ln of x, this is 1 over x. And so that means the integral of 1 over x dx is actually going to be ln x plus c. Now, there's actually something quite interesting here. I think we talked about this in class now, that let me add in here. We'll just do it right here. If we look at the derivative of ln of -x, when we do the derivative, we're going to get, 1 over minus x times -1 by the chain rule. So we still get 1 over x as the derivative. So what is it? What do we get here, right, when we do this integral? Right? Do we get ln of x or do we get ln of minus x? Well, the answer to this, here, this function here is for x positive. This function here is for x negative, right? So we kind of have to think like, well, are we looking at positive or negative x value? The neat thing is we can take this a step further. Since the derivative of x and minus x are the exact same, we can actually say that the derivative of ln of absolute value of x is also 1 over x. And so that leads us to actually say the more general answer here, that was a whole mess of an x. Right? The most general antiderivative we could write down is actually ln absolute value of x plus c. Right? So this is sort of the best answer in general. Right? So the only restriction here is that x can't be 0. That's the only restriction. Right? Cool. So we can sort of combine both of these two into a better version of it. Right? So it's kind of a neat fact there. Let's look at a couple other common rules we had. Say the derivative of e to the x, right? That's just e to the x. So when we integrate e to the x, well, of course, we're just going to get e to the x back, but with our plus c now. A couple other functions here. Derivative of sine is cosine. And so when we integrate cosine, of x, we just get sine of x. But again, plus c. Derivative of cosine of x is negative sine of x. So that means when we integrate sine of x, we actually wind up with negative cosine of x. So again, we can start reversing all of our derivatives here. Okay. So, let's finish out the list a bit here. Let me draw a line here. I'm just going to write down some of these our antiderivatives now. So, secant x tangent x. Right. Do you remember this as the derivative of some function? Well, hopefully you do. This is secant of x. Again, plus c. Secant squared of x. Hopefully you remember this one too. This is tangent of x. And, because it's the greatest function in the whole world, we also have this guy, 1 plus 1 over x squared dx. And this one, we did the derivatives of this. It was kind of an interesting derivative, but the antiderivative of this is going to be the best function ever, arctangent of x. We'll see. Right, so we can take all of the derivative rules we came up with over the last couple weeks and just start turning them all around and get some antiderivatives. Right? So, we'll start doing some work pretty soon. I bet your question here is like, well, what about integral of tangent of x, for example? Right? We don't know a function whose derivative is tangent x, or at least we haven't, talked about one. So we really need to figure out, like, well, what could it be? Okay. We need some additional tools to do this, and that will be sort of topics for the future.